Complex numbers. Now we're looking at complex conjugates and division. When a complex number is denoted by z is equal to a plus bi, there's another complex number hanging around beside it called z bar. And z bar is given as bar a plus bi or a minus bi. It's almost a twin. For every complex number, there's another sort of alter ego hanging around called a complex conjugate. It's almost like a cure. And they have special characteristics. They're really important. When added or multiplied by each other, they yield a real number. So let's just look at these complex numbers and complex conjugates at the moment. Here's a complex conjugate 3 plus 4i. It's 3 out and 4i up. If this was a mirror here, and you imagine yourself looking into the mirror, on the other side you'd get 3 minus 4i. That's its twin. Similarly here, minus I plus I, if you look into the same mirror here, the same real axis, you get minus 1 minus I. And it's almost like the reflection in the real axis. But there's something very powerful about them. If you add complex conjugates together, in this case you've got 1 plus 2i and 1 minus 2i. You just get 2 because they cancel. It's like 1 plus 2i is here, 1 minus 2i is here, and they're mirror images. When you add them, you end up here. It's like 1 east, 2 north, followed by 1 east, 2 south. You either go here and then back, or here and then up. You end up just 2 east away, or 2 real away. So the addition of complex numbers knocks out all of that reflection stuff, and you're back on the standard line. And that's an important line to be on, because that's the real line. This is more impressive, I think. You've got complex conjugates, and we're going to multiply them by each other. 1 plus 2i and 1 minus 2i, and they actually end up on the real line as well. So let's imagine why that would be. 1 plus 2i by 1 minus 2i. Well, we do the FOIL method. So 1 by 1 is 1, 1 by 2i is minus 2i, 2i by 1 is plus 2i, and 2i by 2i is 4i. There's a minus before it, there's an I squared. So now we look at this and we say, they cancel. We're left with 1. The I squared is minus 1, so that's really 4 times minus 1. That's going to be 1 plus 4 is 5. Okay? So effectively, if you multiply 1 plus 2i by 1 minus 2i, or any two numbers at all that are the complex conjugates of each other, you end up that here's one and here's the other. And the answer turns out to be here. 5 plus 0i, which is pretty impressive. Another way of looking at that is this. In the observation of multiplication, we said that multiplication causes the thing to rotate. So if you look at 1 plus 2i, that would force me to rotate this way. But 1 minus 2i would cause me to rotate the other way. Or if you really wanted, call it like that if you wished. But if I rotate up and then back, I end up where I was. Or if I rotate up and then go round again, all that amount, I'll end up to full 360. And that's why it works. It's really neat. It's the only thing that causes something to rotate. And we use that a lot in games for everything. Now we can do division. With division of complex numbers, you've got a complex number on the top, z1, divided by z2. But there's a problem, and the trick is used. You've got one over the other, but what you do is you look at the one on the bottom, the denominator, and you say, I don't want to be dividing by complex numbers. That's a mess. So what you do is, the complex number 2 plus 3i on the bottom, you bring in its twin, the complex conjugate, and you multiply on the bottom by its twin. But you know yourself, if you decide to multiply something by 2 minus 3i on the bottom, you better also do it on the top. So I'm going to multiply above and below by this number here. Now, the bit on the top I'm not too worried about because that's just multiplication. It's going to come out as a number. The bit on the bottom I'm delighted with because when I multiply any number by its complex conjugate, it will be a real number. So let's do the sums. On the top, I get 1 times 2 minus 3i and 8i, 2 minus 3i. On the bottom, 2 times 2 minus 3i, 3i times 2 minus 3i. Now I multiply in, or I expand it out. 2 minus 3i plus 16i minus 24i squared. On the bottom, 4 minus 6i plus 6i minus 9i squared. So it's messy, but it's going to get an awful lot simpler. The first thing I can note about it is that on the bottom I've 6i and minus 6i. That should surprise me. The 9i squared I can live with for the moment. So here I am on the bottom with the 9i squared, and the rest I just copied across. No change there. But what's I squared? Minus 1. So minus by minus would make that a plus. That would make that 24. The 9i squared, I squared is minus 1 by minus is plus. That makes that a plus 9. Is that okay? What did I end up on the bottom with? 13. I don't know if it's right, but it's very reassuring because it's a real number. There's no imaginary bits. If there was an imaginary bit, I'd have made a mistake. Simple as that. Because I knew that when I multiplied something by its complex conjugate on the bottom, it had to be real. On the top, I grouped them together. 2 and 24 gives me 26. 16i minus 3i is 13i. 26 plus 13i over 13, I can now just divide in the bits one at a time. That's a pure number. 13 over 26 is 2. It's 26, and 13 into 13i is I. 2 plus I. So effectively I managed to divide 1 plus 8i by 2 plus 3i. Let's look at how that looks. There was 1 plus 8i, that was Z1. Here's 2 plus 3i, Z2. And here's my answer, Z3. You can see what has happened in division is something that was quite large here, divided by something that's large, made something that was quite small. So in terms of the observation, that's what's happening. Here are the observations now for that. When dividing complex numbers where Z3 is Z1 over Z2, the modulus of the product, the modulus here is the absolute values of the length. What I'm saying is that this was quite large, divided by this gives you this. So the relationship there is Z3 is Z1 over Z2 with the brackets around them, with the lengths. But interestingly, the angles also are there. The angle 3 is the first angle minus the second angle. Not plus, but minus. So what we're saying here is that this angle here, theta 1, the first angle, this one here, theta 2, became theta 3. Theta 3 was theta 1 minus theta 2. Note the minus. In multiplication, it was called plus. What's the difference between plus and minus in angles? Both cause it to rotate, but multiplication caused it to rotate that way, anti-clockwise. The angle we call positive. 0, 90, 180, 270, 360. When you divide, it took it away. Division calls it this way, and it makes it clockwise. So when you want to divide by something, you force it clockwise. So again, if I look at this, it's not as easy, but I'll start on something possibly easier. And let's say I started with the number here, I plus naught. Or sorry, naught plus I. Or maybe here, minus 1. Here. What's minus 1 divided by I? I don't know, but I know that minus I is I squared, isn't it? And what's I squared divided by I? I, isn't it? So that should be I. So if I took this and divided, I'd end up there. What's I divided by I? An easier one. 1. So if I divide this number here, which is called naught plus I, or just I, and divide by I end up at 1. So dividing is clockwise. Whereas when I was multiplying by I kept on moving to the other way. Is that okay? Whereas when I divide by I, I'm going this way. So here's an example. And we talk about it, and we say, here we have it. And we say, there's 1 plus 7i, which is way over here, huge angle. 1 plus 2i, this angle here. I divide this one, z1 in this case, by z2 in this case, and I end up here with z3. The angle was 81.86. This angle was 63. I took one from the other. I ended up with 18.43. So that's how that works.